The purpose of this lab was to observe and gather data for an object's motion at constant velocity with zero net force. In this video, we observed the motion of the biker and the bike system as the biker coasts along a flat parking lot. The axis shown allows analysis for a vector moving in the positive x direction at a constant y value. Shown here, you can see the x-axis with positive x being this way and the y-axis on the left. The video was calibrated using the front wheel of the bike, approximately 2 feet, or in this case, 0.68 meters. This calibration allowed for all our measurements to be measured within meters per second. So as you watch the data as the bike is going across the screen, for the most part it looks pretty linear. The data suggests the biker traveled about 10 meters in 3 seconds, which seems pretty plausible. Therefore, we can go ahead and make calculations for the computer model using this data. Over here, the data allowed us to program our model as accurately as possible. We're able to set the initial position vector at time 0 using this vector, as well as calculate the initial velocity of that time, shown here using the change in position over the change in time. Because the model is supposed to be at constant velocity, this initial velocity should be the same throughout the duration of the video. As seen over here, we can see where we put in our initial conditions. Using the initial position vector as well as the initial velocity vector. The mass used for our model was a combination of both the biker and the bike, making the entire system as a whole 79.38 kilograms. In our model, we used both the biker and the bike for our central position, as shown here. I chose to use a time step of 0.01 seconds because I felt this was enough to give us enough data to get the most accurate predictions for our model without causing it to be too slow. Here we can see our loop was set for the final time in our experimental data, which was 3.065 seconds. And the points are being calculated, or values are being calculated for all points less than this time. Our f of net is set to 0 in order to account for Newton's first law, which states an object in motion will stay in motion unless acted on by an outside force. For this experiment, we are trying to get a constant velocity, which means that there must not be any forces acting to change the velocity, and that the net balance of the forces at work should be equal to 0. Using derivations of Newton's second law, we are able to put in these values in order to find the future prediction of the next point in time, as shown here. So here we're looking for the future velocity for the next point. Then, using this new calculated velocity, we're able to find the new position of the center of the object in motion, with t equaling the new change in time. So now, when we run our model, we see that it looks pretty similar to what we saw in our video. And our graph also shows a linear curve, very similar to the one shown in the tracker video. When we put the two side by side, we can see that there is some source of error. This graph shows that our model position overpredicts the constant velocity, and the experimental data is not quite at a constant velocity. This graph is actually showing that over time, in our experimental data, the velocity is decreasing over time, and the object's motion is slowing down. This can be made more obvious when we calculate the final velocity of our data. So over here, I've copied down the last two values for the time and position of our experimental data. And when you compare the final velocity to the initial, you can see that there's definitely been a decrease, which also further proves that there are more forces at motion and the F of net balance must not be equal to 0. So there are several explanations for this. Several explanations for why this could be, but all must be that the force is acting in the negative I hat direction in order to slow down the object and decrease its velocity. The first error that comes to mind is that the object must be moving fast enough that drag force becomes meaningful and is taken into account. The drag force here would be working in the negative I hat direction and therefore would help to decrease the velocity of the object. Another error in this video could be the duration. Simply the length of the video allows enough time for the friction between the tires of the bike and the surface of the parking lot to come at play, also slowing down the object. Yet another error could occur from the natural topography of the scene selected to shoot the video. If the pavement were to be at a slight incline, not completely flat, then it would cause our model and the experimental data to differ quite a lot because our model does not account for any change in the y position.